So today I want to start the discussion of so-called two-port parameters. We use in RF engineering two different kinds of parameters. One kind of parameter is based on voltages and current, and in earlier days of RF engineering, especially the admittance parameters were used to describe linear networks. Normally, we will also, for example, describe the behavior of a transistor with Y parameters, but then they are only valid for small signals. On the other hand, we have the so-called scattering parameters, and these scattering parameters are based on the incident and reflected waves. And we have later on to discuss also here the newly introduced values, which are called the so-called wave amplitudes, and later I will go in detail to describe or how they are defined. So if I have the Y parameters, we know that we here use the German notation and uses of the errors. So it's very important that you remember that the Y parameters are defined for these directions of voltages and current, and we have in the case of the Y parameter that the current in the input E1 is Y11 times U1 plus Y12 times U2, and the voltage at the current at the output E2, it's Y21 times U1 plus Y22 times U2. So these are the defining equations for the Y parameters of a two-pole or a quadrupole. And what is very essential is, you see there is no voltage defined, for example, from this knot to this knot. This means you have a short circuit here. And the voltage between these two knots is zero. This must be accounted for later if we discuss on about the Y parameters in more detail. So in the case of the scattering parameters, we first must in principle introduce the wave amplitudes. At the moment we don't know their properties, but if I already have defined the wave amplitudes, then the scattering parameters describe the relation between the reflected waves or the waves coming out of port. Here this is, for example, port 1 and this is port 2, and we have for example for the wave amplitude B1, it's S11 times A1 plus S12 times A2. And we will get for the wave amplitudes B2, well, for the wave amplitude B2, this will be S21 times A1 plus S22 times A2. So one of the main difference between the Y parameters and the scattering parameters is that you, in the case of the Y parameters or admittance parameters, they are based on the currents and voltages, so you must be able to measure the current and voltages. While in the case of the scattering parameter, they are defined on wave amplitudes. But waves also exist, for example, in a rectangular waveguide or other waveguides. So with the help of the scattering parameters, we can also describe systems where we cannot define voltages and current, but we only can define waves. So in the next step I will discuss a little bit more in detail the admittance parameters, and then we will go over to the y parameters. So now I want to talk about the y parameters or admittance parameters in more details. I again want to point out, since there's no voltage defined between this node and this node, there is always assumed to be a short circuit between the two nodes. So one normally calls them quadrupole parameter, but essentially they are only three-pole parameters. And here we have the defining equations of the y parameters, and from the defining equation of the y parameters we can now, for example, have a look on how the parameter y11 is defined. So we can, with the help of this equation, we can find for the y parameter y11 that this is the ratio between y1 over u2, but only under the circumstance that u2 is 0. And this is one of the problems which will arise to apply the y parameters at very high frequencies. So we will come to this later. But from its definition, it's clear that we have here the behavior or the notation of the y parameter will be that it's called a short circuit, and you see in principle it's the admittance IC into port 1, so I call this short circuit input admittance. And of course we, in the same sense, we also can now define the other parameters. For example, we can go now to this parameter, say we go to the parameter y22, for example, and y22, according to this equation, is equal to I2 over U2, but only under the circumstance that U1 is again 0. So this is again a short circuit. So we can call this the short circuit. And now we are in port 2 or at the output, so we call it short circuit output admittance. And now we come for a very important parameter, especially if I talk about BGTs. We also will use the y parameters to describe the small signal behavior of BGTs. And we can now, for example, now define the parameter y21. It will be I2 over U1 if U2 is identical to 0. Again, we have to realize now at the output a short circuit for the RF signal, and we call this a then short circuit. And since we have now this parameter describes the influence of the input signal to the output signal, so we can call this forward transfer admittance. Especially in the case of the BGT, this is one of the very important parameters to describe the behavior of the transistor, because we can use the base emitter voltage later on to control the collector current. So, and now we come to the last parameter y12, and this is a parameter. At first perhaps I write its definition. It's I1 over U2. Again, here if U1 it's equal to 0. Also here we have a short circuit. So I call it short circuit. And now this parameter describes the influence of the output onto the input. So we call this, that is the reverse transfer admittance. And we will later on see in the lecture that this is just the parameter which will be responsible for the point that sometimes a transistor can also become unstable. So normally we want to have this parameter to be as small as possible. As I already pointed out, these are the defining equations for the y parameters, and from a mathematical point of view, these two equations are totally sufficient to describe this quadrupole, but the engineers always like also to have an equivalent circuit which is equivalent to these equations. So you see here we have a connection between the output and the input, and as soon as you have a current equation describing the current, then you always can say this is a node equation. So I will sketch here our port 1 or the input, and you see here we have the voltage U1 here, and here the current I1, and you see that the voltage U1 will result in a current which is Y11 times U1. So we can assume that this element here in the input we call Y11, and it's the short put input admittance. So as soon as we have a voltage U1, then of course this element, through this element will flow a current which will be equivalent to Y11 times U1. To describe the influence of the output voltage, we can introduce here a so-called voltage controlled current source, and this voltage controlled current source will now draw the current Y12 times U2, and the same considerations we can also set up for the output. So we have here the output, and there we have the current, the voltage U2, and the current I2 which is flowing into this node. And also you see here you have I2 consists of a current which is due to an admittance and which is times proportional to the voltage U2. So I can write here this element describes now the output admittance, the short circuit output admittance. So you see here again the current E2 consists of a current which flows due to the voltage U2, and also here we have to get the influence of the input. We can again define here a so-called voltage-controlled current source, and this voltage-controlled current source will draw the current Y21 times U1. And this is in principle the one we want to have in a BGT. So perhaps I also draw here, for example, the equivalent circuit for BGT without feedback. So if we would have no feedback or internal feedback, then we will not have any influence of the output onto the input. So without feedback, we will just have here the input admittance I1, and so here we have Y11, and here we have the voltage controlled current source Y21 times U1, and here we will have the output admittance Y22 and here U2. But one must say, of course, this would be the ideal case where we just have an input signal and only the input signal will have an influence on the output, but the output signal will have no influence on the input, and this would mean we have no feedback, and which is identical to Y12 equal to 0. And we will later on discuss especially this case and see, as soon as we have this condition, then the transistor itself cannot become unstable, but this we will discuss in later sessions. Now I want to discuss the problems which arise if we try to measure the Y parameters of a BGT. So here I have drawn a BGT which I brought with this DC voltage source into a so-called point of operation. To bring the BGT in a point of operation, we normally need a resistor RB and here a resistor RC. So the RB resistor normally has a quite high value, so that it will have a very small influence on the Y parameters, but to get rid of the influence of RC, we must introduce here a choke, which means it is an inductance with almost infinite inductivity. So for the AC currents, there will be an open circuit here. And now to feed to the BGT our signal, I introduced here a signal source U1. It's an AC signal source, and I assumed I can realize a capacitor with almost infinite value, and then we will also realize the voltage, the AC voltage here, which is normally then called U1. And for example, now if I want to define, for example, the parameter Y11, we know that the Y11 is given by I1 over U1, but we must realize that the AC voltage at the output has to be 0. So, and how can we realize this again? You see, we must realize a short circuit at the output. This can, in principle, be realized by a capacitor C2. And of course, again, to realize this short circuit, the capacitance C2 must almost have an infinite value. And then we will have here, of course, the current E2 flowing, and also here we will essentially have the current I1. So to define the parameter Y11, we must measure the current I1 with respect to the U1 after absolute value and phase. And also for the parameter Y21, we will have to measure I2 over U1, also realizing U2 must be 0. Again, here this can be realized, at least in a theoretical point of view, by using an infinite capacitance. And now we also see the problems. One of the problems that arises is that the both currents I1 and I2 must be measured with absolute value and phase with reference to the voltage U1. And of course this becomes more and more complicated the higher we have, the higher the frequency is. On the other hand, we have here to realize an AC short circuit at port 2, and this can be realized with a capacitance. But a real capacitance always shows a series resonance frequency, and above the series resonance frequency the capacitance becomes inductive, and then it tends to become an open circuit. So this is not very, it's not realizable up to very, very high frequencies. And we also have another problem which arises if we think about waves. So of course there will enter a wave into the BGT, and this wave will be amplified. And if I have a short circuit at the output of the active device, the amplified signal is then reflected back into our active device. And this results in the point that the active devices tend to become unstable if operated on a short circuit. And these three problems, they are responsible for the fact that we have to use also to describe active elements as parameters at very high frequency. And we will later on see that the S parameters, they don't operate with short circuits, but they will operate with matched circuits at the output and at the input. So all these are reasons that up today in RF engineering, up round about 10 megahertz, only S parameters are used to describe our circuits. Now I want to introduce the scattering parameters, which are based on the measurement of the power of wave. And before we can introduce the scattering parameters, we have to introduce the so-called wave amplitudes, which are unknown up to now. And as an example where we will do this, I take an infinite transmission line, and as we know, on an infinite transmission line there are always two waves able to propagate, one forward traveling wave and one reverse traveling wave. And so I will here introduce the forward traveling wave voltage, the voltage of the forward traveling wave, which will travel in the positive z direction, and also can introduce here the voltage of the reverse traveling wave, which will travel in the negative z direction. So we have the two waves, and we assume here now to have a lossless transmission line, and we define here, for example, the port 1, which is placed at Z1, and I assume that I have here the incident wave amplitude A1, and also we have here at port 2 the incident wave amplitude A2, and we have the reflected wave amplitudes B1 and the reflected wave amplitudes B2. But these amplitudes also will exist on the transmission line, so we will have here the wave amplitude A1, and also here we will have the wave amplitude B1, and again here the wave amplitude A1, and here the wave amplitude B2. Of course, here it must be written A2. So these are the wave amplitudes, and I said already that these wave amplitudes are based on the measurements of power of waves. So we say the forward traveling wave, for example, this carries a certain power, and as a result I will want to get this power as 1/2 A1 absolute value square. So you see here the power of the forward traveling wave is related to the wave amplitude, or we can from this equation write that the absolute value A1 is given as 2 times the power of the forward traveling wave. And in principle, we can also use similar equations to define the wave amplitude B1. So, of course, you see the wave amplitude B1 is given by the power of the reverse traveling wave. So we will have PR, the power of the reverse traveling wave, will be given by B1 square, and also here we would get that the absolute value of B1 would be then the square root of the reverse of the power of the reverse traveling wave. But as you see, with the help of these equations, we are only able to calculate or to assign an absolute value to the wave amplitudes, but we cannot define the amplitudes. So in the next step, I want to compare now this equation with the equation which is valid for our voltage waves. So we can also say that the forward traveling wave is given as 1/2 absolute value 1 over 1 square, but we also know from the transmission line theory that this is equal to 1/2 the absolute value of the forward traveling voltage wave divided by the characteristic impedance of our transmission line. And from this we already can now say that the absolute value of A1 would be equal to the absolute value of the forward traveling voltage wave divided by the square root of ZC. And now we are able to define also the phase by using the phase of the forward traveling voltage wave, or in a waveguide we must use the phase, for example, of the transversal electric field. So I will write this like this. So you see here the absolute value, oh, first I write only the absolute value. It will be the voltage. Of course, this voltage is a complex constant divided by Zc, but now we must assign a certain phase. So we must assign, for example, the phase at Z1 to our A1. So now, as soon as I say A1 is equal to the voltage of the forward traveling wave as Z1 divided by Zc, then we can introduce a phase. And what we do here now, we introduce here a so-called reference plane. So this is our reference plane. Plane of the port 1. So the phase of the A1 is equal to the phase of the voltage, or it's equal to the phase of the transversal electric field at Z1. So in the same manner we can also define now the phase of B1. Of course we see that B1 is equivalent or proportional to the reverse traveling wave, and we can now say the phase, perhaps I write it also like this. First we have the reverse traveling voltage wave divided by Zc, and here again the phase is now the phase of the reverse traveling voltage at Z1. And very similar equations we can set up now for B2 and A2. For example, B2, you see, if I have just a section of a transmission line, then the wave will propagate through this section without disturbing or disruption, and we will get B2 here. And again, you see here it's a wave of the forward traveling wave, the voltage wave divided by Zc. And again, we must here now say that the phase of B2 is equal to the phase of the forward traveling wave at Z2. And also for A2 we can A2 set the same equations. Also here you see A2, it describes the reverse traveling wave. So we have here the voltage of the reverse traveling wave divided by Zc, and the phase is the phase at the point, or the point Zc, or the plane Zc. So also here we introduce a reference plane which results in the fact that the phases of the wave amplitudes are always defined with certain reference planes, and these are denoted by this vertical line. So we are, with the help of these ideas, we were able to introduce the so-called wave amplitudes. They are connected to the, or based on the measurements of the power of the wave, but the phases are assigned by using the phase of the transversal electric field, but this is identical in a transmission line with the phase of the voltage at this plane. So what we did up to now was to define the wave amplitudes, and we used as an example a transmission line which is lossless, and we saw that the wave amplitudes are defined with respect to the power of waves, but to introduce the phases we defined here two reference planes, and we saw that, for example, the wave amplitude A1, the phase of the wave amplitude A1 is given by the phase of the forward traveling voltage wave as Z1, and for example the wave amplitude A2 is the phase of its wave amplitude. It's equal to the phase of the reverse traveling wave at Z2. So in principle we know already all our wave amplitudes. Now I want to deduce the scattering parameters of this lossless transmission line. And to do this, we start with the wave amplitude B2. So we can write that the wave amplitude B2 is nothing else but the forward traveling wave at Z2, and we know that this is described by the exponential function minus j beta Z2. And this can, and we must of course divide this by Zc, but we can introduce now the exponential function minus j beta Z1 times plus j beta Z1. So this is in principle a complicated one, but you see then the exponents will add, and we can write this like this. This is B2 times the forward traveling wave times the exponential function j minus j Z1 divided by Zc. And here you have the exponential function minus j beta Z2 minus Z1. And here I introduce the length, which is the length of the transmission line is the difference between Z2 minus Z1. So this is our length of the transmission line. And here we have nothing else, but this is our wave amplitude A1 at the point Z1. So we can rewrite this as that we have B2. It is now the exponential function minus j beta L times A1 plus 0 times A2. This is due to the fact that, of course, we only have an undisturbed transmission line, and in an undisturbed transmission line, of course, no reflections will occur. So we can rewrite this equation as B2 is now S21 times A1 plus S22 times A2. So we see that in our case the parameter S21 is described by this equation, and in our case S22 of the transmission line is 0. In the same way we can also set up the equations for B1. So we can say B1, you see here, it's the reverse traveling wave, UR, square root times Zc, times the exponential function of plus j beta Z1. And also here we can introduce now the exponential function minus j beta Z2 times plus j beta Z2, and we can now write B1, and then we again rewrite it like this, UR times the exponential function j beta Z2, and also here the difference occurs, exponential function minus j beta Z2 minus Z1, and also here again the length L appears. So this is a length L. So here I forgot to use the square root divided by the square root of ZC, and also here you see that we now have, this is our parameter A2, and we can write for B1 is then 0 times A1 plus, here we have exponential from minus j beta times L times A2. Also here, due to the fact that there is no that we have an undisturbed transmission line, no reflections will occur. So this is the parameter S11 and this is the parameter S22. So in the next step I just want to write the equations again and set up the S matrix. So I've here written the equation again. So we see that it's B11, 0 times A1 and so on. And this is the scattering matrix of a two-part, and if I compare now the elements, we can say the overall matrix of a lossless transmission line is given by the 0, the exponential function of minus j beta L, and here we have again the exponential function of minus j beta times L, and here again 0. So this would be, or this is the S matrix of a lossless transmission line. It's so free of self-reflection, and it's reciprocal, so the influence on port 1 and to port 2 is the same as the influence of port 2 to port 1.